This video covers the basics of graph-based simulation in Proteus by analysing a filter design. The project uses a PIC24 processor to output audio corresponding to the reading on a temperature sensor. The sensor allows adjustment to the temperature and passes the signal through to the ADC pin of the PIC24. The firmware for the processor interprets voltage and reads stored audio from internal memory. The output compare module then carries the AD-PCM signal to the filter. The PWM signal comes in here and passes through the filter to the voltage probe at the output, where we can analyse the clean signal. Let's start by graphing the output waveform. From the left-hand menu, go to the graph mode and select Audio. Left-click and drag to size the graph on the schematic sheet. Tag the probe and simply drag it onto the graph. Right-click and edit graph properties to set time for data capture. When ready, select Simulate Graph from the graph menu at the top, or use the spacebar keyboard shortcut while the graph is tagged. The simulation progress is shown in the bottom status bar. When completed, the audio plays through the computer sound card like this.
20 degrees Celsius.
Double-click the title of the graph for full screen view. We can replay the audio from the Properties dialog to listen for ringing or other artifacts. We can use a frequency graph to better analyse filter performance. Select the graph from the Parts bin and drag into free space on the schematic. Tag the probe, then drag and drop onto the graph. For frequency graphs, we can drop on the left axis for gain or the right axis for phase. Next, connect a 1 kHz generator for a reference signal to the filter input. Add the sine wave reference as the reference generator for the graph. Then simulate using spacebar. In full screen mode, left-click for the primary cursor. Control plus left-click will position the secondary cursor. Using Control and the left mouse button, drag to move the secondary cursor. The measurement and delta values shown at the bottom right can be used to get accurate positioning, in this case 3 dB gain. Shift and left drag allows you to zoom in for greater control. Now we can adjust the filter and retest the results. The changes make a smaller pass band and a softer knee. We then reconnect the PWM and run the audio graph again. We will see high-frequency attenuation resulting in a more muffled sound.
20 degrees Celsius.
Here we have expanded the design so we can compare the performance of the active filter against a cheaper RC filter network. Start by placing voltage probes at suitable points in the filter chain. Right-click and edit the probe names as we go for easy identification. Next, add the probes to the graph. This can be done by right-clicking and adding a trace one by one. Or we can do this using the Quick Add function. Select the graph we want to add the probes to, hold down Ctrl, and click on all the probes we wish to add to the graph. Now add the probes using the command on the graph menu. Run a 1 kHz reference sine wave through the filter for a frequency analysis as before, and use the spacebar to simulate. We can then maximize the graph to analyze the passband and cutoff frequencies for each signal. Even with multiple traces on one graph, we navigate the graph and take measurements in the same way as we did previously. Switch back to the PWM signal for the Fourier analysis. Use spacebar to simulate, and the progress is shown in the status bar. Having maximized the graph, we can use shift and left drag to zoom in on an area as with the frequency graph. 16 kHz is the switching frequency of the PWM signal and is in audible range for humans. We therefore want as much reduction of this component as possible to improve the sound quality. We could also change the trace on the audio graph to listen to the output at any of the various filter stages.